Thank you. Yes, I'll be talking about our work trying to assess landslide tsunami hazard for the Gulf of Mexico, similar to what you've seen in some previous talks. A little bit of background. The Gulf of Mexico coasts have been included in the United States Tsunami Warning System since 2005, even though this is considered a low-risk area, as we've seen from some recent unanticipated events like the 2011 Japan earthquake and tsunami. Even unlikely events, it's important to try to determine the probability or the hazard that could come out of these. In the Gulf of Mexico, the main tsunami generating hazard would be a local submarine mass failure, SMF, which would most likely be induced by an earthquake, a moderately sized earthquake. Then the key issue in our tsunami hazard assessment is the identification of sources, because of course we want to be able to determine some representative source and then numerically model the tsunami generation, propagation, and inundation of coastal cities. However, there's very little data on past Gulf of Mexico landslide tsunamis, so we don't have these historical sources that are present in some other locations. And so for our purposes, a probabilistic approach is really the most appropriate to determine hazard within the Gulf of Mexico basin. So to do that, we implement a Monte Carlo simulation, or MCS technique, to generate 1 million trial scenarios based on distributions for past landslide size and location parameters, as well as sediment and bathymetry and seismicity data. General overview of our MCS method. We first calculate a set of possible landslide configurations based on distributions specifically for depth, area, volume, and length of the landslide. Then we perform a sediment stability analysis wherein we calculate the factor of safety to determine if a slide will fail or not. And then those events which do fail and produce a tsunami amplitude above a certain threshold are considered tsunamigenic. And for our study, we choose that threshold value to be 2 centimeters. So any wave produced over 2 centimeters we consider to be a tsunami wave. And then each of these scenarios can be associated to a certain probability or rate of recurrence. The sediment data that we use comes from publicly available data from past ocean drilling programs. And so you can see all of the dots in there are representative of the locations where data in the Gulf of Mexico exists. And we specifically need data for bulk density and undrained shear strength in our MCS model. And the locations that we choose are 3 distinct locations across the northern Gulf of Mexico, one in the northwest, one kind of in the central, and then one in the northeast. And through each of these, we draw a transect A, B, and C, and within each of these transects, we will use the bathymetry specific to that transect and perform our MCS method. And here's a profile of the bathymetry in each of those locations. And as you can see, transect A and B, which are across the Sigsbee Escarpment in the northwest and central part of the Gulf of Mexico, have very uneven bathymetry, although transect B along the second half of it, where the shelf break occurs, is much more smooth and regular. And we actually split that transect and perform the MCS method for those 2 distinct bathymetry featured locations. And then transect C in the northeast across the carbonate platform of the Florida Escarpment is very smooth, even slope, and has some distinctly different features. The seismicity data that we use comes from the 2014 USGS hazard data, and this map is specifically for peak horizontal ground acceleration, or PHA, of 2% in 50 years. And within the Gulf of Mexico, for any geographical location, we can associate the PHA to a probability, 1 over lambda, where lambda is the return period of an earthquake with that PHA. And so you can see the hazard curve right in the lower right. For any PHA, we can determine a certain probability. And just for reference, within this map, if you can kind of make out, there are, can I use this? There are white spaces, and these are 3 large-scale historical submarine landslide sources that potentially produced a tsunami. And so these are really our historical sources that we can use. And so we placed our transects for the probabilistic approach to sort of try to fill in the gaps and be able to get an overall representation of hazard across the entire Gulf of Mexico. The distributions that we use for size and location parameters come from previous SMF events within the Gulf of Mexico, and these are generally on the smaller scale, with the exception of those 3 large-scale historical sources I pointed out. And we have 27 events that we use, and we associate a distribution to each of the parameters, depth, area, volume, and length, and we see that depth follows a normal distribution. The red dots, or the red squares in these plots, are the actual data values, and then the dashed blue lines are the linear lines for a normal distribution for depth, and then area, volume, and length all follow a log normal distribution. So we also notice within our data that the values for area, volume, and length are very well correlated. You can see here we have volume versus area, length versus area, and length versus volume, and they have very high correlation coefficients. Volume and area have a correlation coefficient of about 0.96, length and area about 0.93, and length and volume about 0.87. And so the new approach that we want to implement is to include these strong data correlations when generating random selections from the appropriate distributions, as opposed to just taking from each distribution a random value for each parameter. We want to maintain these trends in the data. And to do that, we implement a Cholesky decomposition method for correlated random variables. So the Cholesky decomposition approach takes the covariance matrix sigma and decomposes it into C transpose, where C is a lower triangular matrix. And then since area, volume, and length all have log normal distributions, the natural logarithm of each of those variables is normally distributed with a respective mean mu A, mu V, or mu L. And so our method is to first take a set of random normal variables u in the standard normal distribution and determine first correlated normal variables x, y, and z by multiplying the Cholesky decomposition matrix C by our normal variables u and then adding the respective means. And then the random correlated log normal values for area, volume, and length come out of just taking the exponential of those correlated normal variables x, y, and z. And so in this way we're able to form area, volume, and length with those correlations that we saw from the data. So once we have a certain trial SMF location and size determined, we calculate the factor of safety to determine if that specific configuration will fail, and that happens if the factor of safety is less than 1. And the factor of safety depends on the sediment type, the density and the undrained shear strength and the slope, as well as the PHA of the triggering earthquake and the SMF size. And then since it is impossible or computationally prohibitive to numerically model each of these separate events, because we're dealing with approximately 1 million results from our MCS method, we estimate the initial tsunami amplitude eta based on a semi-empirical equation to determine which ones are going to produce the tsunami amplitude that could be hazardous. And this depends on the SMF size, depth, and sediment density. And once again, for those initial tsunami amplitude eta greater than 2 centimeters, which was our threshold, we consider these to be tsunamigenic failures. And then the probability of such a tsunamigenic SMF is calculated as the joint probability of the triggering earthquake, PPHA, and the probability of slide failure, PF, which is the number of failures for a given earthquake return period, lambda, divided by the total number of MCS trials. And then the return period of that individual tsunamigenic event, lambda SMF, is just the inverse of the probability. So here are some sample results for transect A, which was along the northwest Gulf of Mexico across the Sigsbee Escarpment. So this is the output of all of the tsunamigenic results from our MCS method. And these are the plots similar to before for the correlated random area, volume, and length. And as we can see, implementing this Cholesky decomposition approach results in trial scenarios that follow the data extremely well. while still allowing for some natural variability in the sizes. So once we have all of these sample tsunami-genic events, we want to identify the hazard to coastal locations. But we have the return periods of these events are on the order of thousands of years, and so we want to determine what worst case scenario could possibly happen that could be a hazard to a coastal city. And to determine the worst case probabilistic scenario, we find the event with a maximum initial tsunami amplitude eta, as well as a minimum return period or maximum probability. And so we first identify the extreme value of eta for each calculated return period, lambda SMF. Then we select all of the extreme value events with return periods in the first 100 years. So over all of the return periods that we calculate, we take those that happen in the first 100 years, and we consider those to be representative of an event with that specific return period or that specific probability. And then from those, that collection or that set of events, we average the landslide size and location parameters to determine a single worst case scenario event. And to give you an idea of what this looks like for transect A, this is the same plot as before where the blue is the MCS output and the black stars now are that set of extreme eta events in the first 100 years of return periods. And so we see that these are, as we could expect, generally the larger size, though not the absolute maximum because we're looking at the most likely of the large scale events. And then a general overview over all of the transects to see what our expected return periods approximately could be. We see that for transects A and B, we can expect a tsunami-genic SMF event of about 5,000 to 8,000 years. Transect C is quite a bit lower at 600 years. There may be some uncertainty in the data that we're using for that one, so we're currently analyzing that to see where that could be coming from. But just a couple of other things to point out. As we could expect, the shallower the landslide, such as for transect A, the larger the initial tsunami amplitude. And volumes vary, but across transect A and B, across the Sigsbee escarpment, where the very uneven and rough bathymetry was, we have relatively smaller volumes than along transect C, along the carbonate platform of the Florida escarpment. Oops. Well, that was it. So thank you to the National Tsunami Hazard Mitigation Program for funding this important work, and thank you for your time. And I saved you a little bit of effort.
You did save yourself for one question?
Yes.
Are those three variables statistically independent?
The three variables, area, volume, and length.
Volume and area?
Well, we see that they are very well correlated, so there is some possibility that they are not statistically independent, and that's why we implement the correlation for each of those. Does that answer you?
In other